Good morning, everyone. We are going to record this lesson so that you can watch it at your own leisure. And if you're so inclined, you can take a look at the inauguration. So we're covering 8.1 and 8.2 today. 8.1 is a largely algebraic, a couple definitions, just some stuff that we need to know before we can do the geometry. So in 8.1, we start by looking at a ratio. And a ratio is the comparison of two numbers. A score is a ratio. When you say the score of the water polo game was 3-7, that is a ratio of what one team scored to another team. When you look at a percentage on a test, that is a ratio of how many you got correct compared to how many were possible. When we look at the electoral college vote, they could give me a comparison of how many one candidate has compared to how many they need, or a comparison of one candidate to the other candidate. You probably deal with the ratios on more or less a daily basis. On the other hand, a proportion, which I always misspell, so I'm just going to look at it. Yep, that's right. Proportion is the equality of two ratios. So if I have two ratios which are equal, then they would form a proportion. If I were to say the water polo team, we played and we beat the other team 3-7, and the basketball team, or let's go with football team, says, yeah, it's not real impressive. We beat the other team 30-70. I really have no idea how football scoring works. But let's say, oh, okay, well, come to think of it, those two things are proportional. So neither one is a more impressive win, I suppose. 3-7 is 30/70. The way we know that it is correct is with an actual theorem, which we are going to use. And that theorem says if A, and by the way, we have a symbol for proportion. It is this fish-looking guy. If a proportion exists, then, and the book states it a little different than this, but a little different than I'm going to say. It says the ratio, the product of the means is equal to the product of the extremes. Means being the two numbers kind of closer to the center, and extremes being the two numbers which are further out. So 3 times 70 should equal 30 times 7. Of course, they both equal 210, so it looks good. If a proportion exists, then you may cross multiply. And we will actually be using that, oddly enough, in proofs, although not for a while. So the spots in a proportion have names, plural. AB equals C over D. The one that goes here we call the first proportional. This is the second proportional, the third and the fourth. The question I love to ask is if the first three proportionals are 1, 2, and 3, what is the fourth proportional? And without thinking, people yell out 4, but actually what we're asking is 1/2, because the first two proportionals are 1, 2, the third proportional is 3, and what is the fourth proportional? And with a little cross multiplication, we can say, oh, okay, 1 times x equals 6. The fourth proportional would be 6. And 1/2 is the same thing as 3/6. Okay, I am going to do a kind of sub video here explaining something about geometric means, which I put a lot of time and effort into talking about geometric means, but let's just get to the the facts. The geometric mean is the number which I could replace the two means with, the two ones which are closer to the middle, with, and it is the same number. So, for example, if I had 4 over x equals x over 9, x would be the geometric mean of 4 and 9. And solving this is not too hard. We can do our cross multiplication and get that x squared equals 4 times 9, and x equals, you may care about the plus or minus, maybe you don't, x equals plus or minus 6. I usually think of the geometric mean as the positive one, but technically it could be positive or negative. This is actually a surprisingly useful number, both in terms of geometry and just in terms of how life works. And these are weird numbers, but we'll make them kind of a little bit less weird. If a certain employee made $40,000 their first year and $90,000 their third year, then I would expect them to make $60,000 that second year. It is halfway through those two numbers in terms of multiplication. What do I multiply 4 by to make it into 6? 1.5. What do I multiply 6 by to get to 9? Also 1.5. 1.5 times 1.5, by the way, is 2.25, not 3. So if I multiply 4 by 2.25, I get to 9. I spend a little bit of time in this other video, or I will spend a little bit of time in this other video showing how that works and kind of why it's interesting mathematically. Okay, let's move on and let's talk about 8.2. All right, so section 8.2 is about similar figures, similarity. Figures are similar if and only if they meet two criteria. If they have congruent corresponding angles, notice that that's 90 looking and that's 90 looking, and their sides are proportional. And just to remind you, that means that their sides are in equal ratios. So this looks like a square and that looks like a square, and all squares are similar to one another because all squares have congruent corresponding angles. They're all 90, and all sides are proportional. I don't care how big this is. A is to B as A is to B as A is to B as A is to B. All circles turn out to be similar as well. Whatever you want to call this shape, those two things appear to be similar. They are just scale multiples of one another. They got bigger or smaller. In Algebra 2, I refer to this as a dilation, regardless of whether it got smaller or bigger. I do not use the word reduction. So in geometry, we say similar, meaning they are proportional. And in Algebra 2, we tend to say one is a dilation of the other. Okay, I'm going to write those two things down because those are the two big deals here. With an if, figures are similar. Take a look at that symbol. It's like part of the congruency thing. If you want to think of this saying that the angles are congruent and the equals under it for congruent, saying that the lengths are the same, then that's a good way of thinking of it. If figures are similar, then their corresponding lengths are, and remember that symbol means proportional. So which lengths are those? Are those sides? Well, yes, but they're any corresponding lengths. What if two triangles have corresponding altitudes, corresponding medians? Circles could have corresponding radii, diameters, perimeters of shapes. semiperimeters, diagonals, whatever it is, as long as they correspond, they should be proportional between any two similar figures. And this is a little bit more powerful than just saying that the sides are proportional. My other one says if figures are similar, then their corresponding angles are congruent. So these two theorems are really the analogy to CP/CTC. This chapter is very similar to chapter 3, where we learned to prove that triangles were congruent and said once they were congruent, then all of their corresponding parts, whether those were sides or angles, were congruent. Now we say if figures are similar, then their corresponding lengths are proportional and their corresponding angles are congruent. We could write these into a single theorem that way if we wanted to, but I prefer to keep it like this for now. All right. So at this stage of the game, very similar to section 3.1 where we glazed over, in order to prove that two triangles were similar, we'd have to know a whole lot about them. We'd have to know that all three angles of one were congruent to the angles of the other, and those corresponding sides were proportional. Now, again, I can't state this enough. It takes 4 things to make a proportion. Now, some of them could be the same, 1:1 as 1:1, okay? That was just one number used 4 times, but it still needs 4 things. So it never makes any sense to say, oh, is this segment proportional to this segment? Well, it just doesn't make any sense to say that. If this were 2 and this were 7, then they would be in a ratio of 2 to 7. But in order to form a proportion, we would need 2 other numbers. We'd say, oh, well, and this guy has a length of 14, despite what it looks like. This guy has a length of 4. Now I can say, oh, yeah. It seems that 2 is to 4 as 7 is to 14. Or 2 is to 7 as 4 is to 14. Either of those work. Let's see. The book has a theorem which says the ratio of the perimeters of 2 similar polygons equals the ratio of any pair of corresponding sides. For us, that's unnecessary because the perimeter is one of those corresponding lengths. So, okay. I think we are in pretty good shape. How was that for a nice short lesson? All right, guys, if you're watching, please enjoy the inauguration. Other than that, I will see you very sparsely this week. So today is Wednesday at day 5. We X tomorrow, Thursday at day 6. We'll see you again on Friday. Have a good one. Bye-bye.